Hello and good day to you. Today we are going to discuss covariance and correlation. Let's start with covariance. Covariance measures the association between two variables. It helps us to tell whether the variables vary in the same direction or not. We have positive and negative covariance. Now, positive covariance means that the variables change in the same direction. That is, they vary in the same direction. When one is increasing, the other one is also increasing. When one is decreasing, the other one is decreasing. And negative covariance means that the variables change in opposite directions. That is, if one is increasing, the other one is decreasing. And if one is decreasing, the other one is increasing. That is a negative covariance. So as you can see here in this diagram, we have positive, this is positive covariance, and you'll see the teachers' salaries increase with spending in public schools. So you will notice that as the teacher's salary, as the public spending in public schools increase, the teacher's salary also increases. But here we have the child mortality here, and here we have got the per capita gross national product, and you will notice here as the per capita gross national product increases here, the child mortality is decreasing. It is going down. As this one goes up, you will notice that the values for the child mortality is going down. So we have negative covariance here, and here we have got positive covariance. Now, the covariance between two variables, x and y, is denoted as cov xy, and we write it in symbolic form as sigma xy. This sigma is the same one that we use when we are computing the variance, but here now we are talking about covariance, not the variance. And to be able to compute the covariance, it is given by this formula here, the covariance. You first of all get the deviations of each variable from their mean separately. So the variance of x's from their mean, x bar, and the y's from their mean, y bar, and then you multiply those two, then you add. This means you sum. So you sum and then divide by n. That gives you the covariance. So let's illustrate with an example here below. This example shows us the number of newspaper adverts for a company and the sales that they make that correspond to those sales, those adverts, my apologies. So now, to be able to compute the covariance, we first have got to get the differences between these values and the sales and the mean sales, and then we get the sales of the adverts and the mean adverts, and then we multiply them. So first of all, we get the sales, and here you got the difference between, these are for the sales, y, and the mean sales. This is the mean sales obtained by dividing the total here by the total number of values, which is 20, and this one here is the deviation of the adverts from their mean, and their mean is 15, obtained by dividing 300 by 20. And then when you multiply them, you get now the product of your differences in this column here. That's what you get now. These are the products. So you multiply minus 10 times negative 0.49, and you will get this value here. And you repeat all those. And then when you sum, this is the sum of all the products of your deviations. So we can now compute, and if we use the formula that we have, this is how we got the mean sales, and the mean number of adverts. So our covariance will be 365, this one here, and you divide by 20, and that gives you 1.85. What does this mean? It means that there is a positive covariance between the newspaper adverts and the sales, which indicates that the higher the number of adverts, the higher the sales. You should not confuse this one to mean that there is any cost effect relationship. No, we are just saying that they change in the same direction. When one is increasing, the other one is increasing. So this means when the newspaper adverts increase, the sales also increase. When the sales go down, the newspaper adverts are also going down. It's not a cost effect relationship that we are talking about. Now, when we use covariance to measure the association between variables, we have some problem that covariance depends on the units of measure. So the covariance will depend, if we have got large values of x and large values of y, you may find our covariance figure is going to be large. Instead of that, we use the correlation coefficient. And correlation is simply a measure of the strength of linear association between two variables. Now with correlation, we use the correlation coefficient, which is denoted as a law. This is independent of the units of measure, and it ranges between -1 and 1. When rho is equal to 1, then there is no correlation. And when rho is equal to +1 or -1, we have perfect correlation, which means that these variables change. When this one changes by 1 unit, the other one is also changing by 1 unit. So in the same direction if it is positive, but in the opposite direction if it is negative. In between there is going to be correlation, which depends now with the strength. The closer it is to 1, the stronger the correlation of our variables. Once again, correlation, just like covariance, does not tell us about the cause and effect relationship between our variables. Let's again see how we compute the correlation. And the correlation coefficient is computed using this formula, where we have got the covariance. You take the covariance of the two variables and divide by the square root of their variances. So, but now when we are given a set of data from a sample, then we usually denote the correlation as R, and we compute the correlation using the formula R is equal to this is the, you can see this is the covariance here, the deviations from the mean, each variable within its deviation from the mean, you multiply, then you sum. And then here you've got the variance. Variance, you get the deviations and you square them, and then you sum. Here you sum for y, and here you sum for x. Now the n, when it cancels out, when we divide up here, because you are dividing here by n, and you are dividing the denominator by n, the n's will cancel out, and that's why you don't see any n in this formula. So let's example, and we go back to the example of the newspaper adverts. And when we have got in this case, we had already computed the covariance, so we will compute the variances. And the variances, we first of all compute the deviations from their respective means and square them. So this one, you see the deviations of the adverts from their mean, which is 15, and then you square. So these are squared, and then the deviations of the sales from their means, and then you square them. That is what you get. So when we have this, we can now use the formula that we had, and if we now use this formula, because we had already computed this is going to be the value we had obtained for the covariance, the sum of the, not the value of the covariance, but the sum of the product of the deviations we had seen, which we had seen is 36.5, and then this is going to be the sum of the squared deviations of x, which is equal to 1000 here, and this is going to be the sum of the squared deviations of y from its mean, and it's going to be equal to these values here. And so now we input those values in the formula, and so we got that 6.5 you divide by the square root of 1.64762 times 1,000, and what you get is that R is equal to 0.889, which means that we have a high positive correlation between sales and the number of adverts. This means that the higher the number of sales, the number of adverts, the higher the volume of sales, just like we had seen with the covariance. So we can illustrate this one in a graph, and you can see here that as the sales increase, this column is for this is for the sales, and this one is the number of adverts. So as the adverts go up, you can notice that the sales also increase, and that's what we have said earlier. Thank you. This is the end of our discussion on correlation and covariance.